Hi, my name is Matthias Liedtke and I'm from SAP, and today I'm going to present you our development model we developed at SAP for an internal application or an internal server environment application. And the development model is aimed to be compiled both for the CPU and the GPU backend. So first of all, I will start and talk a little bit about the requirements and we had in our environment, our specific environment, and talk a little bit about the related concepts that we already took a look at. And and in the next step, I will present the programming model we have developed. And in the end, I will show some results and see what we were able to achieve with it. Okay, let's start directly with the requirements. And for the requirements, it's a little bit of context is needed. So my team and me, we developed the Erlang compiler. It's a just-in-time compiler, and it is used internally of an existing SAP server environment, and it uses the LLVM backend. So we mainly use it to compile to x86 code and only for x86 and PowerPC. And we provide an internal language. It's called Erlang, and it's a little bit like C and tries to only add a little bit of performance overhead, but adding some safety checks, avoiding out-of-memory crashes and memory leaks in general. So our requirements are mainly ease of use, so it should be easy to use it. So stuff like object orientation or memory management, where we should have some object orientation, and memory management should basically be abstracted from the user. And all that should still be available or achievable while staying at the same performance like a native application like CUDA would be able to achieve, or written in CUDA. We'd like to write it once, so if an algorithm is written for the GPU, we will want to be able to also execute it on a CPU if the GPU isn't available, as we don't have it hardware-wise, or if it isn't available because there's already another job running on it, and we have to schedule somehow our hardware. And the last stuff is that we need some sort of supportability, so it's not worthwhile to have an environment and then you're not able to find errors or profile it. Okay, so here are some existing GPU programming models we have taken a look into. So first of all, OpenMP. OpenMP is, well, you have a sequential program typically, so you have loops and all that stuff. It's sequential, and you add preprocessor directives to that, simple, I'd say it's simple logic that specify how to parallelize this program which isn't parallelized. And for our use case, it wasn't fitting that well because of the limited expressiveness, as the parallelization was added on top of the general logic. So you've written your program in a sequential way. So we took also a look into CUDA, and for the hardware capabilities, CUDA is great because it's it's what is built by NVIDIA, and obviously they support all their hardware features. And there are already a huge amount of libraries for special needs that you can use to not having to reinvent the wheel once again. It also has a C-style interface, but it has little abstraction. So if you want to move memory to the GPU, you have to explicitly move the memory to the GPU. You have to explicitly move it back to the main memory. And here also it's obviously limited to NVIDIA GPUs, so it isn't possible to take the CUDA kernel and just execute it on the CPU. The last one we've taken a look into is OpenCL. And OpenCL aims to be a platform-independent programming model for highly parallel kernels. And so it adds hardware abstractions, so it doesn't matter anymore if it's on an NVIDIA GPU or on a CPU or whatever. And has also a C++ interface and or a C interface too. And it's very close to what we actually needed in our use case, but we had the problem that there was no integration for us. So we would have to put this into the server environment, and due to some restrictions, this didn't really work. So we had to develop our own programming model. And I just start by a simple example. So we are now mixing a little bit of what is the concept of this programming model and an example implementation in Erlang, so our internal language. And so what you can see here is that we define, in the top we define a kernel function, which you can see here. And this kernel function, in this case multiply, it just multiplies data. And below you have the invocation. So the invocation is just a grid invoke, we call it. And yeah, we'll just take a short, more decent look into it. So kernel functions are simply marked by a keyword to know, okay, this has to be compiled for the CPU and the GPU backend. So what we do is we split the code into two binaries, and one we compile for the CPU and one we compile for the GPU. And well, it's all JIT compiled, and then we can call from one to the other. And yeah, so if you have defined your kernel, you can also call it. And well, you need to provide some configuration. It's called grid config in this case. So we have a lot of objects that we introduce. So this pattern is more or less object oriented. So we use objects for a lot of things. Here, for example, for the configuration, where you can just specify how many groups of threads you want, and you can also split it around dimensions if you want to. And then you call the invoke. The invoke just gets the config, and it gets also the kernel function and some arguments bound to that kernel function. So in this case, we have just this array, and yeah, it's bound to the function. So we basically it's passed implicitly to this parameter. And well, what happens with the data? So normally the data is in the main memory. So when you call the invoke function, it has somehow to be transferred. And our idea is that it's transferred implicitly. So what we do is we loop over all these arguments, and we simply copy them to the GPU, we execute the kernel function, and then we copy them back to the CPU. So for simple use cases, it's easy to use, and yeah, you don't have to worry about what to do with the data. Obviously, it doesn't fit all use cases. And so we also introduced a mechanism to override this behavior of copying back and forth every data you want to pass to any kernel. And yeah, the idea is to provide some information to the runtime. And this can be done by a context object. We call it stream. It's defined here. And as long as you have this context object, you have to use it. So in all the cases below, you can see that we use the stream to provide more meaning to it. So we can, for example, in this case, we have two kernel calls. Well, in this case, it's twice the same kernel, twice the same configuration. Doesn't make a lot of sense, but should be, well, you could change it. So you could use a different config, a different kernel, and different data, for example. But if you want to reuse data, like here, the array, it is possible to specify a transfer object, and this transfer object can then be used in multiple kernels. And by defining it, it will simply copy the data to the GPU memory. It will keep it there, will execute all the kernels, and as soon as this object leaves the scope, so here at the end of its lifetime, it gets destroyed, the destructor is called, and the destructor triggers the transfer back of the data of the GPU memory back to the main memory so that the CPU or the regular coding can execute or can access it again. So there we have some kind of more sophisticated data transfers, and it's also possible to extend this to say, for example, if you just want to fill an array with data, you don't have to copy it to the GPU, obviously. So you can also add more context information to that transfer object. Another thing we, when trying to play around with GPU algorithms, is what is needed is always a reduction operation. So as due to the high amount of parallelization, you obviously have a lot of calculations and a lot of results. And in the end, in most cases, you're not interested in a huge amount of results, but maybe just in one or several set of data. And so having a huge parallelization doesn't mean that you want to have a huge amount of results. So you have to reduce it somehow, and this is quite similar to what NVIDIA does with CUP, which is a library for CUDA. We define a reduce operation, and it takes the grid info, so it gets some information about how many threads are there and so on. And then you can specify, okay, what do I want to reduce? How large is the amount? Because you might want to reduce just the warp, so 32 threads, or you might just might want to reduce a group of warps, or you might even say, okay, I just want to reduce every thread into one final result, and this is what we actually do here. So we just say, okay, reduce the complete grid, take the variable, the value that is stored here. It's, in this case, the variable is called partial result, and do this with the following operation. So in this case, we just say add, and well, it will do an add operation internally to do the reduction, and will store the result finally at this location and its global memory pointer. So there it will be stored. And so what is important is that here you can provide any built-in function we offer in our language, but it's limited to all that built-in functions that also have an atomic operation. So for example, for this add, we need an atomic add if we want to reduce more than one warp, because otherwise you would have to handle synchronization, and well, the atomic helps you because it provides a lot of performance while still being able to reduce it. Another thing we found in many algorithms was that there's a lot of explicit locks. So if you want to do a step and you know, okay, I have to wait until I get all the results from the previous step, and I don't want to start a new kernel, okay, I simply create a lock, and I wait until everybody has reached that point. And we didn't really want to have that in our programming model, so we aim to avoid self-defined locks and therefore the possibility of deadlocks. And our concept is that we just have some declarative way of declaring it. So here we have some execution phases, and you can simply declare those phases, and the runtime ensures that each phase is only executed after the other. So only if all threads have executed the load phase, the process phase is executed, and so on. Well, this is basically the program model we have developed, and we have also used it. So not in a productive way yet, but we have implemented a prototype for it and have already some prototype implementations. And what was some of our example use cases was the points and polygon algorithm. And the points and polygon algorithm is basically that you want to know, okay, I have a complex polygon, for example, a specific region in a map or so on in a landscape or whatever, and you want to know, okay, are certain points in this polygon, or are they outside of it? And there's a parallel algorithm for it, so you can see these rays. You can use the point, draw a ray, and if this ray crosses the edges an even number, you know, okay, it's outside of the polygon. If it's an odd number, it's inside. And basically we use that to implement the point and polygon algorithm. And this is basically the performance we achieved. So we have an implementation in CUDA C++, which we would call like the native way of solving it. And then we compare it to our prototype. So our prototype aims to be able to run on the GPU and on the CPU. So we have here the GPU implementation, and you can see the runtime is more or less double of what CUDA achieves. And that was basically more or less the reason, because the algorithm is memory bound, and we don't have vectorized load instructions in our prototype yet. So every load was 2 loads compared to CUDA, because there are lots of points, and those points are 2D. And so we had a lot of vectorized load operations. So we're not quite there, but the performance could be comparable. And for the CPU, obviously, it's an algorithm written for the GPU, and that is what our aim is also, that you write an algorithm for the GPU and run it on the CPU as a fallback or as something to be able to debug it or whatever. And so the performance obviously is a lot higher. The runtime is a lot higher, so we have a factor, so we have 50 milliseconds in comparison to 0.7 milliseconds at CUDA C++. And yeah, but still we are able to run it in a decent amount of time and get results back. And so we are able to also execute those algorithms that are using a huge amount of parallelization a CPU couldn't really handle in a recent amount of time. So some summaries about it. What we were able to achieve is, what our main concepts we had a worker kernel function, which was mainly just marked with a keyword to know, okay, this is a kernel function, and this is comparable to what CUDA and OpenCL do. And for the explicit data transfers, we have this context object, it's called stream, and it's really similar to what CUDA offers with their stream operations. And we also have an object for kernel invocation configuration, which was the grid config to do dimensions and so on. And then when you want to extend this GPU transfer mechanism, you can also create objects, the transfer objects, to override the default behavior by adding those lifetime intervals that also define when the data is located where. On top of that, we have execution phases to get rid of at least most of or some of the locks depending to the algorithm. So obviously there are algorithms where we can't get completely rid of locks, but many are, well, at least you can reduce the amount. And we were able to implement a prototype for it where you have a GPU and a CPU backend using LLVM, and with the focus of the user-defined coding written for the GPU, and we are still able to use the CPU backend and have a reasonable performance there. Yeah, so thank you for your attention, and I'm interested in questions. I'm not really hearing you. Okay.
So the CPU memory you just showed us, is that multi-thread CPU or is that single-thread CPU?
It's multi-threaded. So we have so it's a large machine. It has a lot of CPUs and it uses a lot of that parallelization, obviously. And so the CPU hardware is more expensive than what we use on the GPU side. So obviously it's the worst way, obviously, because, well, you have a parallelized algorithm and you are interested in throughput, so the GPU is the natural target. But we are still able to use multi-threading and use that hardware and reduce the amount of threads so that the CPU is also able to execute it. So our compiler compiles to LLVM IR, and we simply have both backends now in our code base, and we compile one part to the CPU backend, one part to the GPU backend, and then we have some C++ coding that is that takes care of the invocation and so on. So obviously there's some runtime stuff, and that's done in C++. No, it isn't. So we don't have any vectorization on it, and it would be interesting to have that, but well, it's just a prototype status at the moment, so we haven't taken a look into that. But yeah, obviously, if there would be some vectorization, in many cases you would have better performance on the CPU as well.
Here. Okay, thanks for your talk. So you say your programming model tries to avoid explicitly data transfer API calls like appears in OpenCL and CUDA, but in CUDA now they have unified memory models.
Yes. So if you use unified memory, obviously you don't. Well, there is somebody else taking care of it. In this example, the runtime. But the disadvantage is obviously that your data might still be copied back and forth in many cases because, well, you still have to think about it. So you still have to take care about it because if you just access the unified memory, a portion of your memory gets copied to the GPU, then you process it on the GPU, and then it gets copied back if you exit it again from the CPU. So yes, it's right that there is some hardware support for it now, and it's also a great thing to have this, and it might even be something we want to use or to also allow it in our model, but it doesn't solve the problem of that you still have to take care of it. And well, just like in our model, you always have to take care of it because it adds overhead to your coding.
Yeah, so you means that sometimes we still need to manage a copy back and forth. That's that what you mean? Like unified. You mean that sometimes unified memory model didn't help? Or
yes. So well, in our use case, the problem is that we have in our server environment we have our own memory management, and we can't simply use unified memory for all our data. So we still would have to copy our memory from the main memory to the main memory's unified memory, or to a region declared as unified memory, and then having to let the hardware do the stuff. And so in our case, it just doesn't really fit with unified memory. And yeah, but probably in many cases, obviously, you can use unified memory for it.
Yeah, thank you.
Okay, any more questions? Nope, okay, thank you very much.